Okay, so let's start. So before I sort of introduce any other new topic, I thought it would be a good idea to perhaps solve some problems, some easy ones, which sort of uses some of the concepts that we've seen so far. Right? So let's start with some basics of hyperplanes. So let's take something simple. Let's suppose that we have two hyperplanes, right? Let's say A1 transpose X equal to B1. So this defines one hyperplane, the set of all X which satisfy A1 transpose X equal to B1. This is one hyperplane. Let's call this H1. Similarly, this is H2. So when are these two hyperplanes parallel to each other? A1 and A2. In A1 and A2 when A1 is okay, so vector A1 equal to vector A2. And why is that the case? Okay, so why do you say that A is the normal? How do you show that? Say A1 is the normal for H1 and A2 is the normal for H2. Okay. Okay. So let's consider a hyperplane. This is what I'm drawing is a two-dimensional object in R3, and visualize this as a two-dimensional object in R3. And the claim is that this vector A is orthogonal to this plane, right? That's what we want to show. That's what we mean by the normal to that particular hyperplane. So how do you show that it is a normal? Basically, you take any vector which sort of fully lies in that hyperplane, that this vector is going to be orthogonal to the normal. And how do you obtain any any vector which is contained in the hyperplane? You don't have to think so much simpler. Yeah. So take any 2 points. The difference between those 2 points is going to be a vector whose magnitude is equal to the distance between those 2 points, and the angle and the direction is basically whatever. If it's x1 minus x2, then it's in the direction of x2. So if you take any x1, x2 which lie in hyperplane h1, then what is A1 transpose x2 minus x1? So by definition, what is this equal to? 0. So A1 transpose x2 is equal to B1. A1 transpose x1 is also equal to B1 because both of them lie in the same hyperplane. So this is equal to 0. So take any x1, x2 from H1. A1 transpose x2 minus x1 is always going to be equal to 0. So it's always orthogonal. So A1 is, you can call this the normal vector. And if two hyperplanes are parallel to each other, then it must mean that both of them have the same norm. Okay, that's good. So what is the distance between these two hyperplanes? Suppose that A1 is equal to A2, then what would be the distance between these two hyperplanes?
E1 from the norm of A1.
Okay, and why? Yeah, you know it. That's okay. Let's try to view this geometrically.
Here are we assuming A1 and A1 unit vectors?
A1 and A2 are not necessarily unit vectors. No.
They don't need to be equal, but they need to be similar.
Fine. Yes, that's true. So it's parallel if A1 is equal to some constant times A2. That's right.
Yeah.
So let's look at the picture. So you have these two hyperplanes which are parallel to each other, and you have the vector which is normal. So this is the vector which is defined, or the ray defined by the vector A. So if you had to find the distance between these two hyperplanes, just by looking at this picture, how would you do it?
Find the intersection points of the intersection.
Correct. So you know that the angle cut by this ray with the hyperplane is 90 degrees. They're orthogonal. So the minimum distance between these two hyperplanes is basically the distance along this line segment. So essentially all you need to do is find the point at which the ray intersects hyperplane H1, find the point where the ray intersects the hyperplane H2, and find the distance between these two. But what is this ray equal to? How do you find the points of intersection? Let's call this y1, call this y2. be like vector vector plus d times normal vector. What is d? Okay, but
y1 will be some constant times a.
okay, so of course, so
And
first
a
of all,
transpose y is equal to b1, so b is y1.
so firstly, so y1 lies on the hyperplane and y1 lies on this ray. Any point on the ray is basically some constant times the vector a, right? And any point on the hyperplane must satisfy a transpose a1, yeah, a transpose x equal to b1. So then you have you have two equations. You just solve for the unknown. So firstly, y1 should lie in the ray corresponding to a1. So y1 is equal to, let's say, some alpha 1 times vector a1, and y1 also lies in h1. Yes, p1 divided by a square. And so what is y1 equal to? Well, there's only a, right? There's no a separate a1 and a2. p1 times a divided by norm a square. And what is y2? Yeah, same. p2 times a divided by norm a square. Okay, good. So now what is the distance? And what is that equal to?
b2 minus b1 by norm.
Right? Any questions? Okay, that's straightforward. Now let's look at another problem. So a common problem that arises in digital communications is the following. You're given a modulation scheme which you can represent as points in space. In fact, the similar problem arises in a variety of other applications. You're given a bunch of points in space, right? These are essentially points. You can think of these as points that can be transmitted or sent from the transmitter to the receiver. So each message in some sense is mapped to one of these points, and one of these points is transmitted. How it is transmitted, let's not worry about that, in what particular form. But you can assume each transmission to be a vector, which is essentially a point in, let's say, n-dimensional space. Now, once you receive, now what is transmitted is not received exactly. There is some noise. So what is received is some perturbed version of what is transmitted. So what do you do? Typically, the noise is, there are some assumptions on the noise, such that it is Gaussian and so on. So a good way to receive, now what is received is not exactly one of these points. It could be any point in Rn. So what do you think would be a good choice for a decoder? How do you decide which of the points was transmitted? You're given some finite set C. I mean, in let's say error correcting code, C is called the code book. Sometimes in digital communications, particularly when n is very, very small, so C can represent the modulation alphabet. And in many other applications, this can mean something totally different. But basically, you transmit one of the points in C, but you receive some other point, which is some perturbed version of this. So then, how would you decide which point was transmitted? What would be a rule? One point. There's only one point. One of these points was chosen, and that point was set. Okay, so you pick some x from C, and then you transmit, and you receive some y. But what you get is x plus some noise. So what would be a natural, what would be the most obvious way to choose or decide which x was transmitted? So pick a point which is closest to y. It need not give you the correct answer every single time, but that's kind of a natural choice. All right, and particularly it turns out to be the optimal choice when E is distributed according to a Gaussian. So C is known. So maybe I did not clarify that before. Yes, everybody knows C. Okay. But which specific X was chosen from C, that is not known to the receiver. That has to be chosen. That has to be decided.
Do we have a distribution that tells what the y value would be given X?
Right. So that's why if E is assumed to be Gaussian, then it turns out to be optimal.
Should be right?
Which
should not depend on.
Which does not depend on X.
Is E dependent on X?
No, E is generally independent of X.
But then the choice of X won't matter.
It can matter. For example, if E is extremely skewed in some sense, maybe it puts all the weight on in one particular direction, then choosing the closest y may not be the optimal, closest x may not be the optimal choice. So
It's in the expected value.
sure, but in general, let's not worry about all of that. But just the intuition is that if E is Gaussian, then you chose the closest point. So that's what is called a nearest neighbor decoder, right? And that's what we want to focus on, right? The nearest neighbor. Okay? So the decision rule is given. So given any y, so this, you can think of this as the received vector. You choose whatever x hat to be the arg x in C, norm 1. So given any point in space, given the received vector could be any point in Rn, you map this to the nearest point, nearest code word that you can find. So in particular, we are given some code book. So this rule effectively partitions all of Rn into a bunch of different regions. There are no points here. And so, and each of these regions is what is called a Voronoi region. So, so Vi is basically the set of all. So the Voronoi region corresponding to, let's say, the ith point in C is basically that the set of all points in space which are closer to xi than any other xj.
Do you need any way to record times? Like the 2 arguments?
Sure. So 2 points here. Yeah. So what happens when basically it's in the boundary, right? When there's one point which is equidistant to 2 different code words. So firstly, like if it's a random channel, then the probability of that happening is actually going to be 0. Right? That's number one. That's a rare event. Secondly, it doesn't matter. You will never be able to distinguish between those two. So then you can randomly choose whichever you want. And that is typically what is done. Now you could fix an arbitrary rule saying that if it lies on this particular boundary, then you choose, let's say, you choose the left hand, the one which is on the left, perhaps. So any rule is fine as long as you do it systematically. But for now, these Voronoi regions, as the way I have defined them, are not disjoint because they overlap in the boundaries, and that's fine. Okay, but what kind of sets are these? Okay, so it's convex, and why do you say they're convex?
intersection of hyperplanes.
We can take 2 points and so that their convex combination also.
Okay, and you made a point. Hyperplanes.
Are like
Half spaces. Okay, it's a good point. So, and what is that called? I know, but an intersection of half spaces. The polyhedra. So you can view this set, the Voronoi region, as being formed of using multiple decision rules. So firstly, it's the so if this is my xi, if this is my vector xi, then this region is the set of all points which are uniquely closest to xi. Right? So these points are closer to xi than any other point. Right? So that's sort of a global decision. Right? You compare, you find the distances to all other points, and then you choose xi. Now you can also arrive at xi using a greedy rule, in the sense that you pick every pair of points, find which one is closer. Right? Every single pair of points. And when you compare just 2 points, right? Let's suppose that I have one xi and another xj. What is the set of all points which are closer to xi than to xj?
it's a hyperplane split.
Okay, yes. So intuition says that this is a half. Right, so it's going to be the line which splits xi and xj. Okay, so this would be the half space which is closer to xi than to xj. How do we prove that this is a half space? So remember, we had a specific definition for a half space, right? So it's set of all x such that A transpose x is less than or equal to B. Then to show that it's a half space, you have to find A and B. Can you try to find A and B? Okay.
Take any point of diagonal that is assuming to be close to xi.
Okay.
And then show that we project that on line joining xi and xj and show that it is zero.
Okay. I claim that it's simpler. Just try using the definition of h.
Here will be xi vector minus x.
Hmm?
E is norm of x square minus norm of x square.
X square by 2.
Yeah, the midpoint of these two should lie in the x.
Okay. Okay. So hold that thought. How did you get this?
Here is fine.
Sure.
So the A transpose x vector equal to B vector, I substitute the midpoint of these two.
Okay. That's fine, but then you assume that this is a hyperplane. You basically found the hyperplane which passes through the midpoint of the line joining xi and xj.
That will happen.
Yeah. Just think a little, it's not too hard. Okay, by definition, what is h? Or if a point x lies in h, then what should happen? Okay. So that's right, just use the definition. So suppose that x lies in h. Then x minus xi should be less than or equal to norm x minus xj, or this square should be less than or equal to this, right? Great. So what is the left hand side? Just expand the left hand side and right hand side. So this is x minus xi transpose x minus xi less than or equal to x minus xj transpose x minus xj. Right? So x transpose x cancels on both sides, and what you're left with is just linear inequality. So it is just, if I take, let's say, this to the right hand side, then it is, so it's x I minus xj transpose x is greater than or equal to norm xi square minus xj square divided by If you think about it, well, the hyperplane which passes through the midpoint of the line joining xi and xj should indeed be the point that separates the two Voronoi regions, right? So the normal should be on the line joining xi and xj. So that's why the normal is just xi minus xj. And at what point does this line segment intersect the hyperplane? It's basically the midpoint, right? Norm xi square minus norm xj square by 2. So this is for 2 points, right? We pick one pair of points. But then what about the more general case where you have a finite set of points? How do you decide that this is a polyhedron? Yes. If it fits in. Correct. Yes. So the Voronoi region corresponding to xi is the set of all points closer to xi than to x1, x2, x3, x4, all the other xj's. Right. So for every pair, so xi and x1, you have one half space, and the point lies in the Voronoi region only if it lies in every one of those half spaces. Right. So let's say that hij is the half space so to be more precise, hij is the set of all x in Rn such that norm x minus xi is less than or equal to norm x minus xj. So this is for a specific j, right? And vi is the set of all points which are closer to xi than any other xj. So in other words, this should happen for every other j. So this is just the intersection of all the hij. Since there are only finitely many of them, the resulting set is going to be a polyhedron. Any questions? Okay, So a polyhedron is a finite intersection of half spaces. A polytope is a polyhedron which is also bounded. Sorry? A circle is not a polytope. It has to be a polyhedron. It has to be an intersection of finitely many half spaces. Right? So in particular, every polyhedron and every polytope should have a finite number of vertices and a finite number of faces.
The convexity need not be the intersection of finite many.
Yes. A general convex set is an intersection of possibly infinitely many half spaces. So let's now move to a different kind of a problem. So in many problems involving probabilities, you'll eventually have to optimize over probability distributions. So what is basic, but let's try to understand the structure of probability distributions themselves. So let's assume that you have a PMF on this set. This set is just 1, 2, 3 up to n. Right? What can you say about the set of all P sub n? PMFs on it. What kind of a set is this? Okay. Anything more? Okay, let's take n equal to 2. Sorry? It's convex, yes, but what more can we say about it? Yeah? Can you speak up a bit?
Size of the set.
The size, that's true, but again, we're looking at specific types of convex sets, right? We've seen different kinds of convex sets. So what is it? A cone? Is it a fine space? Is it a polytope? Is it a half space? What is it? So there's a name for this specifically, this set. Not sure if you've seen it. You definitely have heard it before. What? No. The simplex. Okay, but okay. Let's look at n equal to 2, right? What does the set look like in R2? So it's a subset of R2, right? So what is P2? Let's write it out formally and let's try to visualize this in space, right? So how would you define P2? It's a subset of, fine, it's a subset. Let's view this as a subset of R2, right? Then what is it equal to? R2 such that? Yeah. So it's P1 plus P2 equal to 1.
0 less than P1 less than P1 1 greater than The line is
Pi is between 0 and 1 for I equal to 1 and 2. Great. So in R2, what does this set look like?
Join 0, 1.
So it's this is my E1, E2. Basically this set. So P3 is going to look yes. What does that surface? What is that surface going to look like? No. It's going to look like a triangle. So it is this triangle. So it's a two-dimensional set in R3. Right? So it's just a triangle with vertices at 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this would be my P3. But okay, fine. So what kind of a set is this? Yes, I know it's convex, but you have more adjectives. Okay, so in terms of the various types of sets that we've seen, what is it?
one half space. This is a half space of expansion.
Okay, let me be more precise. Is it a polyhedron? Is it a polytope? Is it an affine set? Is it a polyhedron? Sorry? Right now I'm just assuming finite n. Because I'm looking at finite dimensional vectors. But yeah, these things can be generalized for infinite n as well. In fact, we can even look at densities. Okay, so is it a polyhedron? Okay, and why? So which half spaces?
Along each of the along every pair of axes, we take the half space 21 and 1.
Okay.
All pair of axes.
Just by looking at this definition over here, can you? Doesn't look like. That's okay, right?
You can just look at that.
Not necessarily. The polyhedron does not have to have a non-empty interior.
They're all Pi plus Pj is not equal to 1.
Yeah. Pi less than
Pi plus Pj is not equal to
A. Something even simpler. I mean, it's there right in front of you.
Pi is less than 1.
Yes, so pi is less than or equal to 1. That a half space? Set of all p for which pi is less than or equal to 1. Is that a half space? What is the A vector? Set of all vectors p. You fix a particular I. Okay? So the set of all vectors p in Rn such that pi is less than or equal to 1. Is this a half space? Yes. And what is the A vector in this case? Yeah, so it's the ith standard ordered basis vector. So it's EI transpose P less than or equal to 1. The same thing. Right? So this is a half space. Okay, so you have n many such constraints. You also have P in Rn such that pi is greater than or equal to 0. Each of these is a half space. And P in Rn such that summation I equal to 1 to n pi is equal to 1. Is this? It's not a half space, but it's an intersection of two half spaces. Right? Summation pi less than or equal to 1 and summation pi greater than or equal to 1. So in other words, you can generate the probability simplex as an intersection of n plus 2, 2n plus 2 half spaces. Questions? So each of these is a half space. Each of these, for every I, the set of all vectors p for which pi is greater than or equal to 0, this is also a half space. So geometrically, what does this half space look like?
So cone at 1, 1, 1, 1.
It's a cone.
Orthid, the negative orthid. And what starting at?
Let's look at just in R2. So P1 less than or equal to 1. Set of all vectors P for which P1 is less than or equal to 1. So it's a set of all points which lie to the left of this. Similarly, the second constraint says that it's a set of all points which is less than or equal to this. The third constraint says that it should be to the right of the P2 axis. The fourth constraint says that set of all vectors which is above the P1 axis. Right. So the corresponding hyperplanes are, so this is one hyperplane, this is another hyperplane, this is one hyperplane, this is one hyperplane, this is another. Okay, so this defines the probability simplex. So it's a polyhedron, but it's also bounded because you demand that summation pi is equal to 1. So it's bounded. Pn is a polytope. Okay, so now this is the set of all possible PMFs. So this forms a polytope. Now, what if we impose additional constraints on the PMF? For example, sometimes you impose constraints such as mean constraints or some sort of moment constraints. For example, the PIs could correspond to the probability of transmission of a particular symbol, and the second moment constraint sometimes corresponds to deciding how much power you're allowed to transmit, right? So let us say that you have the following set. Let's call this A. Such that maybe let's say the expectation of x square should be less than or equal to p, maybe overusing p, less than or equal to alpha, where x is basically a random variable which is distributed according to p. So picking a p is equivalent to picking a random variable because you're just choosing a distribution, and you want to choose a distribution such that the second moment of the power is less than or equal to alpha. So now you're looking at a subset of the set of all distributions. So what kind of a constraint is this? Sorry? Yeah.
Moment constraint.
The integration of linear
There's no integration here, right? It's PMFs on 1, 2, 3 up to n, right?
consider the summation.
Just a summation. So what kind of a constraint is this?
Linear.
Just a linear constraint. So basically, if I just had to expand this out, what is this equal to? I equal to 1 to n. Yeah.
P1 into I.
Right. So it's just I square pi less than or equal to alpha. But I can also write this as 1, 2 square, 3 square, n square p less than or equal to. So this just defines another half space. Right? Any questions? So no matter how you choose, what kind of moment constraints you choose, the resulting constraint is essentially going to be a linear constraint. So all of these are going to correspond to half spaces, and therefore the resulting constraint set will be a polytope. But sometimes you will have other kinds of constraints, particularly when you do information theory, you'll see constraints of the following form. So A is the set of all PMFs on n symbols for which the entropy is greater than or equal to a certain amount, right? And what is this function? It's a function of P is summation I equal to 1 to n pi log 1 over pi. Now this is no longer a linear constraint in P. Do you know what kind of a function h is? Yeah, h is the entropy. It's okay if you've not seen this before, but if you have seen this before, yeah, it's a concave function, right? So it's some kind of a concave function. And if you now I have the following constraint that h of p, the set of all p for which h of p is greater than or equal to alpha. Right? The question is what kind of a constraint? So does this correspond to a convex set? Yes.
Because we have a greater than condition. But
Okay.
had it been less than, we would have
Yes.
but greater than and one case, we have
Sure. And can you always guarantee that?
in this case, yes, never had much.
Yeah. So in we'll see in maybe the next class that if you, the following set. So if f is a concave function, then the set of all x such that f of x is greater than or equal to alpha for any alpha, this corresponds to a convex set. And you can think of it visually, right? So if you have a concave function, then the set of all x for which f of x is greater than or equal to some particular threshold. So a concave function is like a bowl, right? An inverted bowl. And set of all x such that f of x is greater than or equal to alpha is like saying, okay, you take a plane at height alpha and look at the set of all points which sort of lie above this, which correspond to points above this, and that will be a concave. That will be a convex set. These are called level sets, and we'll see them later.
Minus h would be convex.
Sorry?
Minus h would be convex.
Minus h would be convex, yes.
Minus h less than minus alpha.
Yeah.
Talking about on the points above that line. And
So,
between them.
so let me
Okay.
maybe clarify that with an example. So you have x, you have f of x. This is my x. This is my f of x. So this is alpha, right? I'm looking at the set of all x for which f of x is greater than or equal to alpha, which basically corresponds to this interval over here, right? So this is the set of all x for which f of x is greater than. So the set of all x for which f of x is less than or equal to alpha would be the complement of this set. It would be
Not the points which are
no.
situated in the region.
No, it's along the x-axis.
So could you go to which back?
Yeah, just 1 second. Pages back here.
Yeah. So here the dimension of A would be n minus 2, right?
What is A?
Like the set A.
Huh.
But for the next
Wait.
one, it would be n minus 1.
In this case, it would be. Why do you say it's n minus 2? I'm not saying it's equal to alpha, less than or equal to alpha. Right, so this is dimension n minus 1. But if I say that its expectation x square should be equal to alpha, then potentially it's of dimension. Again, it depends on how I choose alpha. If I choose alpha to be very large, then it could include all of Pn. The affine dimension.
Can a function be not convex not?
Yeah. I mean, this is neither convex nor concave. Did you have a follow-up question?
No, actually, I was thinking about this. So if it was a different shape,
Correct. So then you can't claim that the corresponding
concave.
level set is convex. So it turns out that if the function is convex, then the corresponding level sets are always convex sets. Otherwise, the reverse is not true. Okay, so let's look at one last problem. Let's look at cones. So I define this set of co-positive matrices. So it's the set of all matrices A. Let's say symmetric matrices A, such that X transpose AX is greater than or equal to 0, but not necessarily for all X. For all positive vectors. So every component of X is greater than or equal to 0. right? So it should hold for all positive vectors x or non-negative vectors x. Which one? Yes. Not necessarily, right? What is? Okay, right. That's true. Just yeah. But it does not hold for those vectors for which some of the components are positive and some of the components are negative. Basically, all the components of x should have the same sign. Is this a code? Should be simple, because if you take some alpha times, let me call this C. If A is in C, then alpha A is also in C. Right? Because x transpose AX greater than or equal to 0 implies that x transpose alpha AX is also greater than or equal to 0. Okay, is it convex?
Yes.
Why?
Relation alpha a1 plus 1 minus alpha.
Yep, you can take alpha A1 plus 1 minus alpha A2. Okay, is it closed? Here's a hint. If you take any number of closed sets and take the intersection of them, the resultant is always a closed set. Yes.
And it's a convex set, so it's an intersection of half spaces.
Exactly. So of how many intersection of how many half spaces? N. So you fix an x greater than or equal to 0. Right? The set of all matrices A for which x transpose AX is greater than or equal to 0. What kind of a set is this? So what kind of a condition is this as a function of A? So this is a quadratic function in x. But for fixed x, what kind of a function is this as a function of A? It's a linear function. So this is linear in A, and in fact it's equal to the trace of something. It's x transpose times A. Because this is equal to x transpose AX is also equal to the trace of x transpose AX. But then the trace of x transpose AX is equal to the trace of x transpose A. So this is a linear function of A. We are saying that set of all A for which some linear function of A is greater than or equal to 0. So what kind of a set is this? It's a half space. The reason, why not? Because it's a linear constraint. Can you speak up a bit? No, the trace has nothing to do with it. It's just because it's a linear constraint. It is just that this is a nicer way of looking at this because it's an inner product. Right? And what is this set C equal to in terms of Hx? It's the intersection of all the Hx. All right, so let's ask another question. Does it have a non-empty interior? And why do you say that it does?
So we can show that the same way for interior to be X transpose X greater than 0.
Okay, just using that, can you say that this is using what you've already seen without requiring much proof? Superset of? Yeah,
This is a superset.
this is a superset of what set? So this is a superset of, this contains the set of all PSD matrices. The set of all PSD matrices has a non-empty interior. Is it proper? Or the last point left is C pointed. Yeah. So this means that C is a proper pole. So let's stop here, and here's a homework for you. Find the dual cone of C.